Yeah, good morning one and all. Today we are going to discuss the how to design a singly reinforced beam in DDRCS. Okay, so this was the problem which I have taken. Design a singly reinforced beam of clear span 3 meters and support is 200 mm and the working live load 6 kilonewtons and the grade of concrete is 20 and the steel used is Fe415. So with the given data I have drawn the figure here. Now there are 9 steps in this design. So coming to the step 1, cross-sectional dimension of beam. Here the cross-sectional dimensions were not given for the beam. So for that first we have to calculate the cross-sectional dimensions of the beam. Now assume the beam width as 250 because for the beams the range is from 230 to 350 mm. So as per deflection criteria from IS 456 2000 from the clause 23.2.1 for singly reinforced beam the L by D ratio should not be greater than 20. So for that purpose I have assumed L by D ratio as 15 here below 20 it is. Now coming to the calculation of D, L by 15, that is nothing but the 3 meters is converted into 3000 mm, 3000 by 15 I got 200 mm. This was the depth of the beam. Now assume the effective cover D dash as 30 mm. This is also given in the IS 456 2000 table number 16. The overall depth now it is about D plus D dash. D is nothing but the 200 plus 30, I got 230 mm. Coming to the next step, here we are going to calculate the effective span of the beam. Here from IS 456 from clause number 22.2.a, the effective length is given in two clauses. One is L effective is equal to center of supports and L effective is equal to L clear plus D. So we got the answer and we have to take whichever is less. So I have got the same answer, so I have taken the L effective as 3200 mm. Now coming to the next step, here it is about computation of loads. So we all know that the unit weight of concrete is 25 kN per meter square. The self weight of the beam, that is nothing but the dead load, which is nothing but unit weight of concrete plus into width into depth into 1 meter. So I got the value here. Now coming to the live load, which is given in the problem, 6 kN per meter. The total load is nothing but the dead load plus live load, which is nothing but 7.725 kN per meter. Now coming to the factored load, which is nothing but the total load is multiplied with the factor of safety. So I got the total factored load as 11.587 kN per meter. So now coming to the step 4, after calculation of loads, we have to go for the calculation of shear force and bending moment. So the bending moment is nothing but WL square by 8 for simply supported. So I have substituted all the values here. I got the bending moment. And now coming to the shear force, the shear force formula is WL by 2. I have substituted the values and I got the shear force here. Now next coming to the check for minimum effective depth. So which is the formula, which is nothing but D minimum, which is nothing but square root of mu by q into b. So I have for q there is again another formula. So I have calculated the D minimum by substituting all the values which I have gone earlier. So with that I got the D minimum as 133.81, but the D provided is 200 mm. So hence okay, because the D minimum should be 133. D provided D minimum is 133.81. I have provided more than that. So hence okay. Now coming to the next step. Before that there is a reflective question here. So what is the purpose of calculating D minimum? Now coming to the next step, step 6, design of flexural reinforcement. Here we have to calculate the mu is greater or mu limit. With that we have we can justify the section whether it is under reinforced or over reinforced. So to calculate the mu limit, the formula is QBD square. So with that I got as mu is less than mu limit. Hence the section is under reinforced. So the section has to be designed as a singly reinforced beam. For calculating the flexural reinforcement, this is the formula mu. So I have substituted all the values and I got the AST as 2 roots. So I have taken the whichever is less. So the AST for this beam is, AST means nothing but the area of steel, 222.49 mm square. Coming to the next step. So here it is about AST minimum and maximum. There are values from as per IS 456. So AST minimum is 0.85 BD by Fy. So I have substituted the values and I got the value as 122.89, and I have calculated the area of steel maximum. For that also from IS 456 I have got the value. So now AST minimum should be less than AST required and it should be less than AST maximum. Hence the condition is okay for me. So now coming to the assumption of dia of the bars, the main bars in the beam. So I have used as 12 mm dia HYSD bars. So I am calculating the area of each bar. Area of each bar is nothing but pi by 4 into dia square. I got this value. So with that I have calculated the number of bars required for that beam. So in this the formula is AST required by AST of each bar. So I got as 2 numbers. So with this I have came to a conclusion. Provide 2 numbers 12 mm dia HYSD bars as flexural reinforcement in tension zone, and provide 2 numbers 10 mm dia HYSD bars as hanger bars in compression zone. Coming to the next step, here it is about the design of shear reinforcement. The main reinforcement calculation is completed. Now coming to shear reinforcement. From IS 456-2000 table number 19, the nominal shear stress tau V is equal to Vu by Bd. So with that I have got the value of nominal shear stress, and the percentage of tensile steel is 100 AST by Bd. So with that I got the percentage of steel as 0.37%. So with that table I will take the value of tau C. So here I have got the tau C value as 0.42, which is greater than 0.39. So the shear reinforcement is not required. If it is vice versa, the shear reinforcement is required. But meanwhile we have to provide the minimum reinforcement for the beam in the form of vertical stirrups. So now coming to the design of vertical stirrups. So from that IS 456 clause number 26.5.1.6, use 8 mm dia for stirrups, we all know that. So use 8 mm dia HYSD bars, 2-legged vertical stirrups. For that we have to calculate the spacing. So spacing formula is equal to 0.87 Fy into ASV divided by 0.4 B. So I have substituted the value and I got the spacing as 302. I have rounded to 300 mm center to center. So in that again the clause is maximum spacing. From IS 456-2000 clause number 26.5.1.5, for beams there is a maximum spacing which is nothing but 0.75 D or 300 mm. Take whichever is less. I got the maximum spacing as 150 mm. So conclusion, provide 8 mm dia HYSD 2-legged vertical stirrups at the rate of 150 mm spacing throughout the beam as the shear reinforcement. Coming to the next step, it is nothing but the check for deflection. So whether the beam is able to stay with the deflection or not. So for that the formula is L by D maximum is equal to L by D basic into KT into KC. So the KT and KC values are defined from which are nothing but the modification factor for tensile reinforcement and modification factor for compression reinforcement. So with this I have calculated the KT and KC values from IS 456-2000 figure 4 and 5. So I got the value of KT as 1.3 and KC as 1.1. I have substituted in this formula, and I have got L by D maximum is greater than L by T provided, hence it is okay. Now coming to the reinforcement details which I have obtained through the problem, I have shown in a figure. So this is a longitudinal section and this is the cross section. So reinforcement details at the bottom 12 mm dia 2 numbers HYSD bars, and at the top 10 mm dia 2 numbers as anchor bars or hanger bars, and the vertical stirrups 8 mm dia 2-legged vertical stirrups at the rate 150 mm center to center. So hope you all understood this design of a singly reinforced beam with the 9 steps. Thank you.